In this lesson, we're going to talk about power and sample size. So specifically, we'll define power. I'll give you an example for computing power, and I'll use JMP software for doing that. We don't really compute this by hand. And lastly, I'll show you some SAS code. So power in hypothesis testing is your ability to detect a difference when the difference is actually there. So that's going to fall into this kind of decision table here. So the decision here is fail to reject H naught, reject H naught, and then the top here tells you which of the hypotheses is true. So of course, if we fail to reject H naught and the null hypothesis is true, we're making the right decision. Okay, and so we have a probability of that of 1 minus alpha, where alpha is your significance level. If we make the decision to reject the null hypothesis when the null hypothesis was true, that's that type 1 error that we talk about, and that's the one we usually set to 0.05 for most hypothesis testing. Another option is that you fail to reject the null hypothesis when the null hypothesis is actually false. So you should have favored the alternative, and you actually failed to reject the null. This is a type 2 error, right? So you failed to pick up that the difference was actually there, and that's what we call beta. Now the last option is the one where you're actually correct. So for that one, you reject the null hypothesis when in fact the null is false, and that's a correct decision. This corner right here is power, and that's what we're talking about. Again, your ability to detect a difference when it's actually there. So in order to talk about this, we're going to talk about it in terms of the kind of inputs to power. But before we do that, I'm going to use JMP to kind of give you a little bit more of an idea about power. So what's going on with this one is we have a scenario where the red distribution here is the hypothesized mean. So we're hypothesizing that the mean is 65 when the true mean is actually 68. Okay, so if we think about it here, we're going to test whether the hypothesized mean, which is 65, maybe we're doing a one-sided test here to test whether the mean is actually greater than 65. Oops, sorry, 65, not 64. Okay, so this red distribution here, the red distribution is the hypothesized mean, and the blue distribution is the true mean. Now, there's actually the estimated mean in here too. It's right here, and it doesn't really matter what the estimated mean is. That's kind of an important idea because with power, your main idea with power is you're usually doing this before you actually collect your data. So you're figuring out the power of your test, you're figuring out your sample size before you've actually collected the data. So you don't really know what your estimated mean is yet because we haven't got the data. So under the null hypothesis, right, we're assuming that our distribution is here centered at 65. We, for a power and sample size scenario, we have to actually know what the true distribution would be. And so we're assuming that it's actually bigger than 65. And this turns out that it's centered at 68. Okay. So if you're doing this, you assume that you have drawn data from this red distribution right here, right? And if you get any data that's above this, where we have 0.05 here, you're going to reject the null hypothesis, right? And in this case, we're saying it's true. The true mean is actually bigger than 65. So if we're here or beyond, we're going to make the right decision. However, if we are here or beyond, this is going to be a type 2 error. We're going to fail to reject the null when we should have rejected it. However, the chances of actually being here are pretty low, right? Because if, in fact, the true distribution is centered over here at 68, the bulk of this distribution is here, right? The tail kind of goes out here, and that's much lower. So that's why this blue area here, that's the type 2 error. You'll notice that your beta here is very small, okay? That's because these distributions have this much separation. Okay, so one of the things that plays into power is how big of a difference do you want to be able to detect? If the difference is very small, these are close together, you're not going to have as much power. If they're spread out, it's easier to detect that scenario. Okay. The other thing that also plays into it is your type 1 error, right? If you make this bigger, okay, so that's going to raise your power because you have less of a chance of having that type 2 error. Okay, so again, you can kind of see that if I move these distributions away from each other, you'll notice that my beta is going down, which ultimately increases my power. But as these two distributions move closer to each other, we now have more area in the blue and my power goes down. Okay, so that relates back here on what really goes into the power and sample size calculation. So here, since we're talking about completely randomized designs, this is a one-way ANOVA sample size calculation, and you can think of our sample sizes in one-way ANOVA as replicates. So again, a frequent question is how many replicates should I use? And we can do that using power. So it turns out that increasing the number of replications, which is increasing your sample size, increases your power. To determine the number of replicates, which is usually the question when you set out to set up your design, is you need to first set the desired power level. Okay, so here, this is normally set to 0.8 a lot of times. A lot of times people will have 80% power. If the power increases, your sample size is going to increase. If your power goes down, your sample size won't be as high. But again, usually this is just an input, and most of the time I've seen people have 80% or higher for that power. The significance level is again for your hypothesis test, we just looked at that, and it's usually set to 0.05. The effect sizes, if you're thinking about those two distributions and how far apart they are, the effect size is telling you how much what the size of the difference you wanted to detect. So you saw as that size got smaller, the power went down, and as the size got bigger, the power went up. And so we've got to have some idea about the effect size. Sometimes this is a hard question, and some studies use the rule of thumb that a 1 standard deviation change in the mean results in a biologically important difference, so they can take that into account when they're doing the power and sample size. The last thing you need, which can also be difficult, is you need an idea about the natural variation in your study. So again, I'm telling you haven't done your study yet, but you have to have an idea about variability. This estimate can be obtained from maybe a pilot study, maybe a literature review. You saw where someone else had done a similar study, and you take their mean square error from their ANOVA analysis, and you use that in this kind of natural variation. Another kind of maybe less scientific, but it's at least an input, is you could use this where you have the range of the data for a given treatment and you divide by 4. And this relates back to the empirical rule, because if you think about the empirical rule, it says that 95% of your data should be within 2 standard deviations of the mean. So that spans 4 standard deviations. So if you want 1 standard deviation, you would divide by 4. The reason you don't divide by 6, because with 6 you would have 99.7% of your data, is if you think about it, that's lowering your variation estimate. And so again, with the 4, we think we're being more conservative here. But again, this would kind of be my last resort. I would use this other information if I had it. So let's look at an example. A researcher is designing a project to study the yield of pecans under 4 rates of nitrogen. The researcher knows that if the average pecan yields differ by more than 15 pounds, there's an advantage in using the treatment providing the higher yield. So they want to determine the necessary replications to be 90% certain that the F-test will reject, and hence detect a difference in the average yields whenever any pair of nitrogen rates produce pecans having average yields differing by more than 15 pounds, and they set alpha to 0.05. So everything that's important here is you have your alpha of 0.05, you have your 90% certain that it will reject, that's your power, right? We know that we have 4 groups, that's important to know, and then a difference of 15 pounds. The only thing that's not in this part is our idea of the background variation. So if you look at it, again, 90% power, significance level is 0.05. The effect size is the minimum distance of 15 pounds, right, for that advantage. And then the assessment of sigma, some additional information is from a previous experiment, the researcher knows that yields have ranged between 40 to 70 pounds. So they're going to use that rough estimate of sigma again. the one I said isn't the best, but you could use it. Sometimes people have a better idea about the range of their data than they do variation. So we're going to use 7.5 here as our estimate of the standard deviation. Now at this point, usually I have another tutorial that says this is how you do this in JMP. We don't calculate these by hand, so I'm going to pull JMP in here. You can use R, you can use any software, but I think it's still, even if you're an R user, important to listen to the rest of this just so that you can talk through some of the important pieces that will be important in R code or other software. So in both JMP and SAS, and also in many of the R packages, you must adjust the mean values for each treatment group. The reason that's the case is because you have to, those mean values will tell JMP or the software how many groups you have. And they look at those mean values to figure out the effect size that you're trying to detect. So in this example, the researchers are interested in detecting a change of 15 pounds, and we know that there are 4 treatment groups. I will tell you that the hardest situation to detect is if 2 of the groups differ by the difference you want to detect, and the other groups are right in the middle. Okay, so there's no separation between the other groups. So for this, we could say that one group was 0, one group's 15. That's a difference of 15, right? And then the other 2 groups are right in the middle at 7.5. Arbitrary. I pick those out because it's easy for me to take 0 as one group, add 15, and then I can go to the middle. I'll show you how you could use another set of different or values here, as long as they differ in the same scale, that will get the exact same results. If you understand this, I would say if there are 5 groups, then the 5th group, if we still wanted to have a difference of 15, would also be set to 7.5. Okay, so let's go ahead and let's pull up JMP. You're going to go into DOE, Design Diagnostics, Sample Size and Power, and the PowerPoint gives you this as well. We're going to go to K-sample means. So we said for our standard deviation, we were setting that to 7.5. And for our groups, I don't really ever change the extra parameters here. I'm going to put in 0, I'm going to put in 15, I'm going to put in 7.5, and 7.5. All right, so there are my 4 groups. Again, if I had 5 groups, I'd put it in at 7.5 again. And for my power, I'm going to put it in at 0.90. Okay, so if I continue here, I get a suggested sample size of 33. Now that's 33 total for all 4 groups. So sample size is the total sample size per group. You'd have to divide that by 4. So if we go back here, again, this is all set up here. We could use the about 8.25. So we said if we have 9 in each group, we could use that. And so I'm going to say that we do have 9 in each group, that we actually decided to do 9. If I get rid of power here and hit continue, then it'll tell me that my power is up to 93%. That should make sense, right? Because I'm using more replicates than what it suggested to begin with. You'll also notice in the notes I used some different values. So I just wanted to show you here that you get the exact same results. So if you say you wanted to use 40, 55, because that's more on the range of the data that you were seeing with this this study, and then you put this in at 47.5 and 47.5 because that's the average of those two. If I get rid of this, put this back to 0.90, I'm still getting the 33. So again, I think it's easiest to put 0, 15, 7.5, 7.5. It doesn't matter as long as 2 of them differ by the difference you want to detect. The other 2 are right there in the middle. Then you have the exact same thing. I could call this 140, 155, 147.5, and 147.5. If I get rid of this, I'm still back to 33. Okay, so again, I like the case. I think this is the easiest. The other thing I wanted to show you is if this were to happen to increase, right, then what do you think is going to happen to the sample size that's suggested? It's going to increase as well. So you can play around with this dialog box to be able to figure out what's suggested from a sample size calculation. And then the last slide shows you some SAS code. You'll notice that this is very similar to what you just saw in JMP. And our packages are also the same. You leave the one blank that you want it to solve for. And that pretty much wraps up calculating the number of replicates for a CRD.